Okay guys, Unit 4, Lesson 6. We are now going to start also exploring the graphs of tangent and cotangent. And I know in 3U that we sometimes really briefly look at the graph of of tangent, but we don't do much with it. And now we're going to also take a look at cotangent. So our learning goal. I understand what the graph of tangent looks like, given the relationship it has with sine and cosine. I can use my understanding of reciprocal functions to graph cotangent, and I can apply transformations to these graphs as well as others. So part of this lesson is going to be here. It's just a very short part, and then the second part is going to be on Desmos, but we just have to get through this first little part first. So, given the diagram below, determine the ratios for sine theta, cos theta, tan theta. And here we have a right angle triangle, and we have 12 and 5, and this is a triangle where we can find the hypotenuse by saying that the hypotenuse, which is the longest side, is equal to under the square root 12 squared plus 5 squared. And that's 144 plus 25, which is the square root of 169, which is exactly 13. So we have this 5, 12, 13 right angle triangle. So sine theta is opposite over hypotenuse, which is 12 over 13. And cos theta is adjacent over hypotenuse, which is 5 over 13. And tan theta is opposite over adjacent, which is 12 over 5. So there's a reason that we're doing this. We're going somewhere with this. And now, using these ratios, I want us to look at what sine theta divided by cos theta is. So if we have sine theta, that's 12 over 13, and I could do divided by 5 over 13, but you can see that that's a bit of a mess. So when we have division of fractions, I always recommend that we write them with our division statement, or our division symbol. So 12 over 13 divided by 5 over 13, and then our fraction rules tell us to keep the first fraction, change the sign to multiplication, and flip the second fraction, which is now 13 over 5. And then our cross-canceling rules tell us that these guys can cancel each other out, leaving us with just 12 times 1, or 12, in the numerator, and 1 times 5, or 5, in the denominator. So sine theta divided by cos theta is equal to 12 over 5, and interestingly, or maybe not for you, tan theta is also equal to 12 over 5. So, therefore, and we are in Unit 5, we're going to look at trig identities, and this would be like your first trig identity, and you guys should already know this, but just as a recall. So, therefore, tan theta is equal to sine theta divided by cos theta. So we can use this idea of our very first trig identity to help us investigate what the graph of tan theta is going to look like, given the graph of sine theta and cos theta. And that's what we're going to do with this. So, given that tan theta is equal to sine theta divided by cos theta, use the graphs of sine and cos below to predict what the graph of tan will look like on the interval negative 2 pi to positive 2 pi. So here we have the graph in yellow is our sine theta, and in blue is our cos theta. So let's just start on the y-axis. And so what we are going to be doing is taking any of our sine values. Okay, so we're going to be doing sine values divided by cos values to give us our tan value at that corresponding point theta. So if we were talking about at 0, which is on the y-axis, we would be doing a sine value of 0 divided by a cos value of 1. 0 divided by 1, 0 divided by anything is just 0. So tan is going to have a coordinate at 0, 0. Let's move forward to pi over 2 and see what's going to happen there. We're going to have sine, which is 1, divided by our cos value, which is 0. Well, 1 divided by 0 is always going to result in an error. We cannot have that. And therefore, what we learn from rational functions is anything that makes the denominator equal 0, anything that makes cos theta equal 0, is going to result in a vertical asymptote. And so we could take a look here and see exactly where we're going to have vertical asymptotes. So let's get my dotted line out and some sort of color, and know that this graph is going to have a vertical asymptote at negative 3 pi over 2. Okay, so I'm kind of jumping around now because anywhere where cos theta is equal to 0, we're going to have a vertical asymptote on tan theta because we can't do whatever the sine value is divided by 0. So that's going to happen here. It's going to happen at negative pi over 2. We're going to have a vertical asymptote. It's going to happen again at pi over 2, which is the one we were just investigating. And it's going to happen again at 3 pi over 2. So now we already know that our graph of tan theta is going to have vertical asymptotes every pi, as we multiples of pi as we go up by pi. But starting at, we could say pi over 2, okay? But in both directions. So we've got vertical asymptotes. Now let's take a look at some other important points that might help us draw this. Where's my pen? There we go. Okay, so we've already investigated 0. We've got what's going on at pi over 2. Let's take a look at pi. So here at pi, we have a sine value of 0, and we have a cos value of negative 1. It doesn't really matter because 0 divided by anything is just 0. So we just put vertical asymptotes everywhere where cos was equal to 0 because that's when we have 0 on the bottom. Remember, from rational functions, anything that makes the top equal 0 makes the whole function equal 0. So we could also go ahead and say anywhere where sine crosses the x-axis, our tan function is going to have a function value of 0. So over here, we are going to have a function value of 0. And over here, we're going to have a function value of 0. Okay, so great. We've got a bunch of x-intercepts, we've got a bunch of vertical asymptotes, and now we need to figure out what's going on beyond the x-intercepts before the vertical asymptotes in either direction. So let's take a look at between 0 and pi over 2. So between 0 and pi over 2, let's just say here, this would be pi over 4, which is going to be right in the middle here. This would be pi over 4. So at pi over 4, notice that the functions have a point of intersection there, which means they have the same function value. And when you divide anything by itself, you get back 1. So this is 0.5, this is 0.1. Let's just say it's like, it's not 0.75, but let's just say it's close. 0.71 divided by 0.71 is just going to be 1. 0.75 divided by 0.75 is just going to be 1. So no matter what, at pi over 4, which is right here, tan has a function value of 1. And again, it will have a function value of 1 for any of the times that we have that point of intersection. So that happens again over here, because a negative divided by a negative becomes a positive. So even though now we're dealing with like negative 0.71, negative 0.71 divided by negative 0.71 is going to be positive 1. So again, this is pi, and that's 3 pi over 2. So in between here and here, right in the middle, we have that function value of positive 1. Again, they have a point of intersection over here between negative pi over 2 and negative pi. So again, we have a function value of 1. And maybe you're noticing the pattern that to the right of that x-intercept, but to the left of the vertical asymptote, they all have a function value of 1. So over here, same thing, we're going to have that function value of 1. And now we need to choose a point where we can investigate what's happening between or to the right of the vertical asymptotes, but to the left of the x-intercept. So let's take a look at, it doesn't really matter where, but let's say from 0 to negative pi over 4, okay? So on this interval, what is really important is that on this interval, sine is negative, okay? Sine is negative, and cos is positive. And when we have a negative divided by a positive, it gives us back a negative. And so the function values are changing, but if we wanted to estimate at exactly negative pi over 4, let's just say it's somewhere around here and somewhere around here, we'll notice that it's likely going to be the exact same function value, except for one is a positive and one is a negative. So if we take the negative and divide by the positive of the exact same, we're just going to get back negative 1. So right between here and here, we're going to have a function value of negative 1, and that's going to be the case for all of them to the right of the vertical asymptote and to the left of the x-intercept. We have this graph that looks something like this, and we could go beyond, but we just needed negative 2 pi to positive 2 pi. Okay, so now we have something that looks like this, and maybe you already know what tan looks like, so maybe you can already fill this in and you're like, this is a very long investigation when I already know, but if you don't, I think it's really important to understand why tan looks like it does. It helps us to understand the graph and the function. So we're coming from this way, we're going up, and we're going this way, okay? And that's just it. On repeat between these vertical asymptotes, and I'll show you a nicer version of this in a second, but basically that's just what it looks like. It's just this same pattern repeated over and over again. And this is not a sinusoidal function. It doesn't have that wave-like pattern, but it does repeat. The period of tan is not 2 pi. It is repeating every pi, right? As we go up by 1 pi, go up by 1 pi, go up by 1 pi. So the period of tan is actually pi, not 2 pi. And because it's not sinusoidal, it has no amplitude, because it doesn't have a max or a min, so it has no amplitude. It has x-intercepts at the multiples of pi as we go up by pi, pi, 2 pi, 3 pi, etc. It will have x-intercepts. It has a y-intercept of 0. It has vertical asymptotes starting, let's say, at pi over 2 and going up by that period by intervals of pi. So that's what we know about the graph of tan, and if we take a look here, that's exactly what it looks like, which is what we came up with. We have those x-intercepts happening regularly. We have, at those intervals of pi, we have those vertical asymptotes happening intervals of, or increments of pi, but starting at pi over 2. We have that positive 1 value happening between the x-intercept and the vertical asymptote, and we have that negative 1 value happening between the vertical asymptotes and the x-intercepts on the other side. So there is exactly what the curve looks like. And using what you know about reciprocal functions, now we are going to come up with a guess of what we think the graph of cotangent might look like. So I'm going to give you a minute to pause the video and think about what you think might be